Within science, the rules that govern the macroscopic universe, such as planets, stars, and galaxies, could not fully explain the behavior of the very small. And by very small, we're talking on the atomic level and smaller. Quantum mechanics grew out of the general weirdness we see at that level, and some of the ramifications of quantum theory are mind-blowing to say the least. Quantum mechanics is very weird in comparison to how we viewed reality before, well, quantum mechanics. Richard Feynman sums it up best when he said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." April 14th is World Quantum Day, as 4.14 just happens to be Planck's constant if you round it up to two significant digits. This is a fundamental constant in quantum mechanics, though we are going to avoid as much math as possible, as I suspect I will lose half my viewers every time I drop a formula on them. In today's video, we are going to examine 5 pretty awesome things about quantum mechanics, so settle yourself into your favorite chair or chairs across multiple universes as we jump right in. The double slit experiment was first run all the way back in the early 1800s as Thomas Young wanted to design an experiment to prove that light was a wave and not a particle. Trust me, that was all the rage. If a wave moved through a double slit, it would create interference that would lead to 3 bands instead of 2 on your detector. Of course, in 1800s, your detector was pretty much looking at light on a wall. Now the 3 bands, 1 band from each of the slits, so those are 2, but then the 3rd band in the middle, well, that would be caused by the interference as waves of light were interacting with each other. Of course, we now understand that light can be both a wave and a particle. If we move forward to 1961, Klaus recreated the double slit experiment, but instead of light, he fired electrons, and the results were interesting as he got the same wave pattern on his detector. In 1965, Richard Feynman suggested that electrons must likely have a dual wave property. It would not be until 2013 that technology would allow us to redo the experiment, firing single electrons to hopefully figure out what was going on once and for all. Instead, we only made things weirder. When we fired a stream of single electrons at a double slit, we once again received the same interference pattern. However, this is where it gets a little bit funky. Once we observed each electron moving through the slits, the interference pattern vanished, and the electrons moved like a particle and not a wave. It seemed the very act of observation impacted the behavior of a single electron, of a whole stream of single electrons. This does sound pretty weird. However, you do have to remember, to measure something means that you have to interact with it in some way with your observation sensors. Thus, the electron technically does know that it is being observed. This does not make it any less weird, and it's just our first reason as to why quantum mechanics is awesome. Near the very end in the death of a star, not destined for a supernova explosion, it still loses the fight with gravity and collapses as nuclear fusion has stopped within that star. Gravity then pulls the star's material inward, and things begin to get very dense. You might want to think that the star can just collapse forever and maybe become a smaller black hole, but that is not what happens at all. The collapse is eventually halted by something called electron degeneracy pressure. Electron degeneracy pressure is a form of quantum degeneracy pressure, which is closely related to something called the Pauli exclusion principle. Wow, it is beginning to sound like we can use an aspirin sandwich. In very simple terms, the Pauli exclusion principle will not allow 2 electrons to occupy the same quantum state. So as gravity tried to push these same electrons with the same quantum state together, this degeneracy pressure pushes right on back. The end result is that the star collapses down to about the size of our Earth and then becomes what is known as a degenerate dwarf, or more commonly called a white dwarf star. A white dwarf is no longer able to produce energy, so eventually over a very long time it would cool down and eventually become something called a black dwarf. However, this is a process that takes more than 13.8 billion years, the age of the universe, so we have not yet seen one. To understand Hawking radiation, we first need to look at virtual particles. If you have empty space with nothing in it at all, is it really empty? The answer is no, as fluxions within the quantum field allow for virtual particles to pop in and then back out of existence. These particles come in pairs, where one is a particle and the other is an antiparticle. Normally they come together and annihilate each other, thus returning to nothingness. Stephen Hawking theorized that if these virtual particles appeared near the event horizon of a black hole and then get separated by gravity, one of them can fall into the black hole, while the other can escape as something we now call Hawking radiation. The extreme gravity the virtual particle experiences while falling into the black hole would provide that particle with negative energy, and thus that virtual particle would remove mass from the black hole. I guess that means a black hole can get smaller. The concept is mathematically sound and has a lot of support in the scientific community. To date, we do not have firm observable data to prove Hawking radiation exists, and it will be hard to measure. However, as our instruments get better, it is only a matter of time before we know for sure if it is real or not. When it comes to weirdly awesome, quantum entanglement has to take the cake. This is a phenomenon that Albert Einstein called spooky action at a distance, so you know it means business. So what is quantum entanglement? In a nutshell, you can entangle two particles by basically bringing them together and allowing them to link up or entangle. Once two particles are entangled, it means they have a relationship between an emergent property such as spin that aligns. So if you were to take one of those particles and change its spin, the spin on the entangled particle will also change. But what makes it spooky is that you can entangle the particles, then take one of the particles and put it on a spaceship that then takes it, let's say, 5 light minutes from Earth. So if you then change the spin on the particle that's still on Earth, the spin changes on the particle on our spaceship. Why is that weird? Well, the spaceship is 5 light minutes from Earth, thus light would take 5 minutes to reach the ship. But yet the change in spin took no time. This action, it appears to violate the speed of light. When I first heard about entanglement, I thought, well, this is pretty darn cool because we could use it to communicate with an eventual colony somewhere in space. Well, the answer to that is yes and no. So far, we do not have the ability to manipulate entanglement in any way that we can actually send data with it. There are scientists working on it, and if they are someday successful, it could open the door to some pretty nifty technologies, even beyond faster than light communication. We are talking about quantum internet, insanely hard quantum cryptography, and quantum teleportation. Trust me, the level of awesomeness in quantum entanglement is absolutely unlimited. It all begins with a cat. Schrodinger's cat is a thought experiment where a cat is put in a box. There is also a vial of poison in that box that is set to break open if a detector observes a random subatomic event that may or may not occur. While we watch the box, we do not know if the cat is dead or alive until we open the box. So before we open the box, that cat can be thought of as both dead and alive, existing in a dual state. So which state is valid before we open the box? Well, obviously both states are valid. From the cat's perspective, though, they can only experience one state, and that is the one in which they are alive. The other state where they are dead is no longer observable. The only perspective of the cat after the box is opened is in the reality where the poison has not broken. Okay, so does this mean both realities are valid? With the many worlds interpretation of quantum mechanics, that would be a huge yes. The many worlds interpretation implies that any time there is a chance for different outcomes, all outcomes occur across many worlds. In effect, the reality we are in splinters off. If you think of every possible choice or outcome ever, we are quite literally looking at an uncountable number of splinters of reality, of very many worlds indeed. Sure, that is cool, but what about the perspective of that dead cat? The idea of quantum immortality is that any choice that leads to a dead end will end the splinter that cat is on. But for that cat, they are also alive on the splinter where they live. So as far as that cat is concerned, everything is okay and it is time for a belly rub. With a person, if you are in a situation where there is a chance you could die, you will die and you will live. On the splinter where you die, everyone on that splinter will be sad and all of that, but you will be on that other splinter. You will be on that splinter where you will continue, and thus you are like, phew, that was a close call. The idea of quantum immortality gets a little more complicated when you deal with every variation of outcome, because you may live, but you may be permanently injured in some splinters. Obviously, they are all still you, but some of you will have different challenges, and who's to say if you are on that splinter or one where you completely sidestep that falling piano? This is a theory I do not think we have any way to really prove, but it is a fantastic thought experiment, and it is kind of awesome to think about. If you love science content, be sure to subscribe to this channel, and if you like this particular episode, be sure to time dilate that like button. Be back here next week when we will once again get our science on for another video.